Imagine a power grid where not a single watt of energy is lost to heat. Right now, about 5 to 10% of all electricity simply vanishes into thin air because of the resistance in our copper wires. For over a century, we've known about superconductors, materials that carry electricity with zero resistance. But there's always been a catch. They usually only work at temperatures colder than deep space. But in March 2026, researchers at the University of Houston changed the game. They found a way to make a mercury-based material superconduct at a record-breaking 151 Kelvin, or minus 122 degrees Celsius. This isn't just a small step, it's a leap toward the holy grail of materials science. At 151 Kelvin, we are moving away from expensive liquid helium and toward much cheaper cooling methods. The material at the heart of this is a mercury-based cuprate. It's a complex ceramic layered with copper, oxygen, and mercury atoms that creates a perfect highway for electrons. But the real magic isn't just the chemistry, it's how the Houston team forced these atoms to stay in a state they normally hate. They used a process called pressure quenching. To understand why this is so clever, you have to realize that most high-temperature superconductors only work while they're being crushed by massive pressure. The moment you let go, the property vanishes. Imagine trying to hold a spring compressed with your bare hands. It only stays that way as long as you're applying force. The Houston team found a way to glue the spring shut. By quenching the material under 300,000 atmospheres, they froze the atomic lattice into its high-performance state, allowing it to work at ambient pressure. When they released the pressure, the material didn't revert. It stayed a superconductor. This is the first time we've seen a mercury cuprate maintain such high performance in normal conditions. The result is a material that exhibits the Meissner effect, the ability to repel magnetic fields at temperatures that were previously thought impossible for stable compounds. It's a physical demonstration of zero electrical resistance. If you start a current in a loop of this material, it could theoretically flow forever without losing a single electron. But achieving this required a machine capable of generating pressures found deep inside the Earth's mantle. This is where the engineering gets truly extreme. How do you crush something with the weight of a mountain on a laboratory bench? The answer lies in the hardest material known to man: diamond. Next, we're going to look at the diamond forge, the specific mechanism that allows us to rewrite the rules of atomic physics and lock in these impossible properties. To reach 300,000 atmospheres, engineers use a diamond-anvil cell. It works on a simple principle: pressure equals force divided by area. If you make the area small enough, the pressure becomes astronomical. The tips of these diamonds are polished to just a few hundred microns across, about the width of a human hair. When they press together, they create a tiny pocket of extreme physics. Inside this chamber, the mercury cuprate isn't just being squeezed. Its very atomic structure is being reorganized into a more efficient configuration. At 300,000 atmospheres, the distance between the copper and oxygen atoms shrinks. This overlap allows electrons to pair up into Cooper pairs more easily, which is the secret to superconductivity. Think of it like a crowded hallway. If the atoms are spaced out and vibrating, electrons keep bumping into them. That's resistance. But under pressure, the atoms form a rigid, silent corridor. The challenge is that once you remove the pressure, the atoms usually spring back to their messy, resistive state. This is where the quenching part of the process comes in. Quenching is a technique borrowed from blacksmithing. By rapidly changing the environment while the material is under stress, you can trap it in a metastable state. In the Houston experiment, they used a specific thermal cycle. They heated the sample while it was under 300,000 atmospheres and then rapidly cooled it before releasing the pressure. This locked the atoms into their high-pressure positions. When the diamonds were finally backed off, the material remembered the pressure, maintaining its superconducting properties at 151 Kelvin. To prove it worked, the team performed the ultimate test: the Meissner effect. They placed the quenched sample in a magnetic field and watched as it completely expelled the flux. The sample didn't just sit there, it levitated. This isn't just a trick, it's proof that the material has become a perfect diamagnet, a core characteristic of a true superconductor. Even more impressive was the resistance measurement. Using a 4-point probe, they confirmed that the voltage drop across the material was exactly 0. This is the highest temperature ever recorded for a superconductor that doesn't require active external pressure. It's a massive milestone, but it's not the finish line. Because while the physics is brilliant, the material itself presents some massive engineering headaches. We're talking about one of the most toxic elements on the periodic table: Mercury. Next, we have to look at the industrial reality. How do you take a process that happens at the tip of a diamond and scale it up to power an entire city? Mercury is a fantastic ingredient for superconductors because of its unique electron configuration. But in a world moving toward green energy, using a potent neurotoxin is a hard sell. If a mercury-based power line were to fail or be damaged, the environmental cleanup would be a nightmare. This means the engineering of the cables themselves has to be overbuilt for safety. Engineers are looking at ways to encapsulate the material in incredibly tough, flexible polymers that can withstand impacts without ever letting the mercury escape. Then there's the scaling problem. A diamond anvil cell creates a sample the size of a speck of dust. To be useful, we need miles of this stuff. We can't just make bigger diamonds. They become exponentially more expensive and prone to shattering. Instead, engineers are looking at multi-anvil presses that can crush larger volumes. The goal is to move from batch processing to continuous processing, essentially a high-pressure rolling mill that can quench the material as it's being manufactured. Even with these hurdles, the potential is staggering. A lossless power grid would change everything. We could place solar farms in the Sahara and power London without losing a single watt in transit. It would also revolutionize transport. Maglev trains using these 151 Kelvin superconductors would be much cheaper to operate, potentially making high-speed rail as common as the bus. And think about computing. Data centers currently spend 40% of their energy just on cooling. Superconducting processors would stay cool naturally, leading to a new era of supercomputing. The University of Houston's breakthrough proves that the pressure quenching technique works. It's a new tool in the material science toolkit that we can apply to other, less toxic materials. Maybe the next breakthrough won't use mercury at all. By using the same lattice locking physics, we might find a room temperature superconductor hiding in plain sight. We are learning how to forge materials not just with heat and chemistry, but with the raw, crushing power of the stars. The path from a tiny diamond anvil in Houston to a global energy revolution is long and full of challenges. But for the first time, we have a map. Next time you see a power line humming in the wind, remember that we are on the verge of making that hum and the heat that causes it a thing of the past. The world of 151 Kelvin is just the beginning. The future of engineering isn't just about building bigger, it's about crushing atoms until they do the impossible.